take you through a practical example of generating an emulator of an atmospheric radiative transfer model called Lintran. And Lintran is often used in operational retrieval schemes for the greenhouse gas methane. The workflow introduces you to the multi-layer perceptron algorithm, which is a supervised neural network algorithm. With the multi-layer perceptron neural network algorithm, we aim to predict tropomi radiant spectra in the shortwave infrared, which is the band that is often used in order to retrieve methane. And with this, I propose to start and jump right into the practical workflow. So we are in week 5, where we introduce you to machine learning examples with an atmospheric application. And the example I will introduce you has the topic number 5C, and we are in this specific folder. And you see here in this folder we have one Jupyter notebook, a data set which is provided in the format .npset, and a pre-trained model which we will make use of during the workflow. And with this, we can start. So as already said during the introduction, atmospheric radiative transfer models are often used in order to retrieve greenhouse gas concentrations such as methane. And these radiative transfer models can range from simple to very complex, and especially more advanced radiative transfer models are often computationally heavy and can take a long time to run. And this makes it often very unfeasible to use in operational contexts. And this is the motivation of this workflow, to see how advanced radiative transfer models can be replaced with emulators or statistical models that approximate the advanced radiative transfer models. And in this context, emulators essentially learn from the physics of the advanced radiative transfer models and are generated using a statistical model that learns the output modeled by radiative transfer model. And this notebook takes you through an example of generating such an emulator of an atmospheric radiative transfer model called Lintran that is often used in operational retrieval schemes for the greenhouse gas concentration methane. As input data for generating the statistical model, we use 50,000 simulations of the Lintran radiative transfer model, and these simulations have been performed by Dr. Landgraf from the Dutch Space Research Organization. And here you see a table that indicates the key atmospheric parameters and their value ranges, which were used as input into the Lintran model to build the emulated training data set. We also linked a set of additional articles and research papers you can have a look that introduce you to radiative transfer models, methane retrievals, greenhouse gas concentration retrievals, etc. And with this, I propose we start, and we start as we always start by importing a range of Python libraries we will make use of during the workflow. We use the multi-layer perceptron algorithm provided by the scikit-learn package, and this is what we do here. So we load the MLP regressor class, but additionally we also make use of some other functionalities of the scikit-learn library in order to scale data and also to evaluate the model performance. And here we load a set of helper functions to load the input data, for example, and also to calculate specific metrics in order to evaluate the model performance. So the first step is to load the training data set, which is provided in a .npset file, which is a zipped archive of different input parameters. So the first step is to load the training data set, which shall be used to train the neural network. And the file methane_dataset is a npset file, which is a zipped archive of different variables. The file contains the following parameters. It contains a state vector, which are atmospheric parameters that are used as input for the radiative transfer model. Then WL stands for wavelength of the output radiance values in the tropomi shortwave infrared band. Then spectra, which is the radiance spectra output from the radiative transfer model. Additionally, we also have parameters number of data sets, which provides us the size of the data set or number of simulations, and number of params, which is number of atmospheric parameters used in the study. We can use the function or the helper function load data to load the file and also retrieve already the parameters individually. And this is what we do here. So we provide to the function the path to the data set. And what a function does is it returns the 5 variables individually. And if we inspect the shape or the dimension of each of the variables, we see that the state vector, we have 50,000 simulations and 125 atmospheric parameters, which are used as input for the radiative transfer model. The wavelength are 834 values in the tropomi shortwave infrared spectra or shortwave infrared band. Then the spectra, we have again 50,000 simulations, and for each of the simulation 834 radiance spectra output. And then number of simulations is 50,000 and number of parameters is 125. And as a next step, it's good to visualize one example of the Lindran simulated tropomi radiance spectra in the shortwave infrared band, and this is usually the band that is used to retrieve methane. And if we visualize it, so we see here the tropomi radiance spectra in the shortwave infrared, and we can see certain absorption and scattering features resulting from gases and other atmospheric parameters such as pressure and temperature. And this is the simulated tropomi radiance spectra in the shortwave infrared created by the Lindran radiative transfer model. As a next step, we now want to split the training data, which we just loaded, into 2 subsets. One subset we want to use for training the algorithm, and the other subset we want to use for validation and to validate the model performance. So the next step is to split the sample data into training and validation subsets, and we can do this by applying the function train_test_split from the scikit-learn library. And the function takes the following keyword arguments. It takes the input parameter for the machine learning model, which in our case is the state vector, so 125 atmospheric parameters that are used to simulate the radiative transfer model. Then the output parameter, which is in our case the spectra information and the variable spectra. And then additionally, we also provide to the function the test size. So this is a percentage or a relative percentage of the sample data to be used for the validation. And in this example, we want to use 10% of the sample data for validation. And the random state keyword argument helps us to ensure reproducibility, and we set the random state to 0. A test of the error sizes of the training input and also validation input allows us to see that out of the 50,000 simulations, we now use 45,000 for training and 5,000 samples are used for validating the model performance. The next step is now to standardize or scale the input and output parameters. This is a very common process or operation in machine learning, especially if we have a very diverse range of different input and output parameters. So standardization or scaling of training data is a common operation in machine learning, especially if we have diverse input parameters with different data ranges. And so different functions can be used for standardization or scaling, where the optimal scaling function depends on the type and distribution of the data set. And so for this reason, it is always advisable also to have a look at the distribution of the input data. In the case of the training data we just loaded, most of the data have distributions that are unimodal or bimodal with either tail-heavy or normal distributions. And for this reason, we scale the data by centering the values around the mean with a unit standard deviation, which removes the mean and scales the data to unit variance. There are also other scaling techniques, such as data normalization, in which values are shifted and rescaled to that they end up ranging between 0 and 1. Otherwise known as min-max scaling. This approach is good to use when you know that the distribution of your data does not follow a Gaussian distribution. In this case, we apply the standard scaler, also from the scikit-learn library, and specifically of the pre-processing module. And this class helps us to scale data based on the data's mean and standard deviation. And so first, we construct a standard scaler, and then we fit the scaler to the data with the function fit, and eventually we transform or scale the data with the function transform. And this is what we do. So first we use the output data, the output training subset, so spectra_training. We construct a standard scaler, we fit it to the spectra_train, so the training output data, and then we transform both subsets. So we transform the training output and also the validation output. And then we repeat the same scaling process for the input data, for the training subset and the validation subset. And this is what we do here. We construct a standard scaler, we fit it to one of the subsets, and then we transform the training subset and the validation subset. Before we can set up and train the neural network, we have to do one additional step. And this step is applying a principal component analysis to the output spectra. Due to the large amount of the output variable, the spectra information we have, it is advisable to apply a principal component analysis in order to reduce the redundancy and collinearity in the wavelength. And this is what we do here. So we use the PCA constructor that is also part of the scikit-learn library, and we apply it to the scaled training output data. In this example, we want to set a number of principal components to 20. And so this means, as a result, the dimension of the scaled training output data is then reduced from previously 45,000 times 834 to 45,000 times 20. So we then have only 20 principal components instead of 834 wavelength information. And this is what we do here. So we construct a PCA by providing the number of components, and then we fit it to the spectra_train_scale variable. And then we transform it. And if we check the dimensions, we see here that the dimension reduced from previously 834 wavelengths information to 20 principal components. And now we can set up and train the neural network. So the next step is to define the neural network architecture, and this workflow introduces you to a NLP regressor. And this class is also part of the scikit-learn library. And the NLP regressor is a multi-layer perceptron supervised neural network algorithm. It is quite easy to construct a NLP regressor, so we just use the NLP regressor constructor, and then we provide a set of hyperparameters, which we listed here, and also including a description of what each hyperparameter and keyword argument specifies and is doing. We don't go through all of them now, but I highly recommend you also to see the documentation of the NLP regressor for additional parameters you can set. So this is a very standard setting of the NLP regressor, what we have here. You can apply the function get_params, and this allows you to get a dictionary of all the set hyperparameters, and this is also what we did here. So we get a list of all the parameters or hyperparameters set to the NLP regressor constructor. The training process of the model is often called fitting, and we can use the function fit to train the model based on the training input and training output data. So we use the scaled input data, which are the scaled atmospheric parameters, 125 atmospheric parameters, and as output we use the training subset of the output data onto which we also apply the principal component analysis. And this is what we do here. So we apply the function fit to the input data and the output data. We set a number of 600 iterations, and this is why we add here a note. So this can take quite a long time. And for your convenience and also for this example here, we already pre-trained a model. For this reason, you can also go to the next step where we already load the pre-trained model in order to show you how you can also evaluate the model performance. But feel free also to run the fitting or training process, and we also provide you here an example how you can save a trained model. You can use the function dump from the library pickle. After the training of the neural network algorithm, the next step is then to evaluate the model performance, and this is what we do now. So after the training of the NLP regressor, the next step is to use the model and predict these spectra based on the validation data set. And as a first step, we want to load the pre-trained model, and the model is called NLP regressor_model, and this model is also provided here in the folder. And you can use the function load also from the pickle library to load a pre-trained model. And this is what we do here. And you can then also apply the function get_params, and then you see also the defined hyperparameters on which the model has been trained on. And the next step is then to predict the spectra with the loaded pre-trained model and the validation input data set. And this is what we do here. So we apply the function predict and we provide the validation input data set to the function. And the output are the predicted spectra information. But because we applied a scaling and also principal component analysis to the input data for the training, for this reason we also have to inverse the transformations in order to evaluate the model performance. We can use the function inverse_transform for the classes PCA and also standard scalar to inverse the transformations for the predicted spectra. And so first we inverse the principal component analysis and then we inverse the scaling. And this is what we do here. So we use the PCA class we defined, and then we apply the inverse underscore transform function to the predictions, and we take the output from here to the scalar spec constructor, we apply the inverse transform function, and the result are the predicted true values. And now we can evaluate the model performance with the predicted spectra and the true spectra we get from the radiative transfer model. And so once the transformations of the predicted spectra have been inversed, we can continue to evaluate the model performance. We can evaluate the model performance by comparing the predicted spectra with the spectra from the validation data set. And so two common metrics to measure the error of the model are root mean square error and normalized root mean square error. And these two functions have been defined at the beginning, and both functions take the validation and the predicted spectra as keyword arguments. And here we compute both metrics, and we first compute the accuracy of the training, which is around 62%. And then we see here the root mean squared error and also the normalized root mean squared error, which are acceptable in this case. And as a last step, we can visualize the predicted spectra output from the neural network algorithm with the true spectra information that came out of the radiative transfer model. And this is what we do here. So we visualize the predicted results and compare it visually with the model output. And first we can visualize the outputs of the radiant spectra from both the Lintron RTM model and the predicted one from the neural network. And we see here in black the predictions from the neural network, and in red the true spectra information from the Lintron radiative transfer model. And you can play around here because it takes different number of simulations, and you can see also for if you let it run differently, for some of the simulations the fit is better, and for some the fit is not so good. So here you see a bit of divergence. This is quite a good fit. So feel free to also play around here with different index values and the different fittings. And then as a last step, we can also visually inspect the residuals, and the plot shows here that the mean error is roughly around 0, and this is in general a good result. Of course, there are certain wavelengths that have a bigger error, but most of the wavelengths have an acceptable error. And now we arrived at the end of the workflow, where we introduced you to a multi-layer perceptron algorithm, which is a supervised neural network algorithm. And this workflow showed you how you can use a neural network to create an emulator for an atmospheric radiative transfer model.